Can you see?
Yes, sir.
Shana?
Yes, sir.
Okay. Okay. Castigliano theorem. So this is not continuity of last few weeks. So this is just new lesson. Uh, the Castigliano theorems, we can uh, find out the deflection of the beams. So you can easily find out the deflection using this theorem. So when it's on the beam, if there is a load applied, so you can find out the deflection in the vertical direction or horizontal manner, or so the resultant deflections likewise. So this is the theory. So in this theory, so you will already strain, how to find out the strain energy. So can you tell me what is the equation for the strain energy? So anyone? The very first lecture we will discuss. Strain energy is normally labeled as a U. A Chenal law for me. Is it okay if it is wrong? Just as you remember.
U equals sigma squared over 2e.
Sigma square
Over 2e.
2e. Yes. So that is the strain energy equation. So um, so we will use that equation in different format. So you can eliminate elastic modulus from that equation, or else you can eliminate sigma terms, or you can introduce epsilon terms likewise. So because sigma equals e epsilon, so according to that manner, so you can substitute sigma o epsilon with other two terms. So you can use that equation different format, but basic equation as well. So strain energy. So what is the meaning of strain energy? When you apply the force on the element, so it will be deformed. With the deformations, we call it strain. So applied, we will do the work on that element. So that work will be absorbed as a strain energy. So that is the theory. So then we will discuss about the Castigliano theorem. So we will use strain energy theory for the explain the Castigliano theorem. And there is a, when you solve the equation using Castigliano theorem, so you need to use some mathematical relationship or rules. So there is a one rule, so we call Leibniz rule. Don't worry about the name of another thing. So just this is kind of a like chain rule in the differential equations. And normally integrations and differentiation, you will use a chain rule and different type of rules. So this is kind of rule, Leibniz rule. And then in the Castigliano theorem, there is a way to find out the deflections at particular point. So when we find out the deflection at different point, you will use some theory. So you don't know, but so when you use that theory, you need to some kind of load at that point. So normally we will use dummy load if there is not exit load at that point. So that is the use of dummy load. And then the different kind of approaches using that theory you can see during this topic. So as I told you, strain energy this topic. So we can see there is a different type of load apply, mood of load apply on the element. So can be constant force during the time. So with the time it is constant, you can see. So this is with the, this is not the x-axis is not the time, but with the time force is constant, so same extension also increase, you can see. So constant load. So this is normally we call creep. So during the creep failure, so this is the thing normally happen. The constant load apply, with the time it will be strain. So that's the thing. So we can find out the work done on this system by area under this curve. So f time x. So that is the strain energy also we can say. So if it is not waste to different form, but we assume there is no any other form like heating or something like that. So if there is sound, it is also waste as this work will be waste as like that, but we assume those terms are zero. So then it's the strain energy. And the linear force, we already discussed this in the first lesson. Okay? So linear force, you can see with the time it is increased. So according to that manner, this way also will be increased, the linear way. So work done by system, work done on system, you can see the area under this curve, it is half of this. Okay. So in the nonlinear condition, we are not normally discussing during this under this module. It is not this state. So you need to focus on the advanced type of calculations, but in this level we are not going to discuss with nonlinear force. So you can see so how the variations with the constant force and linear force. So you know how to find out the work under this kind of force. So if it is nonlinear, half of fx. So we already discussed these things. And yeah, when an elastic body is deformed, work is done on this that system, and stress, that sigma is proportional to the strain. We already know sigma equals E epsilon. That's why we call that equation. And strain energy used up is stored in body as strain energy, which is given by. So we already know this equation, but not this format. So I will write down in here. So you know this equation as Fermi told. This is the equation. Sigma is square. Sorry, I'm sorry. I'm sorry. Two A. So this is the equation. As I told you, we can rearrange this equation. So we can substitute E with the sigma and epsilon. So if it is sigma and epsilon, this is sigma divided by epsilon. So we can cut sigma with this sigma square, and epsilon will be here. So this will be half epsilon. So different manner you can arrange it. So same thing. And you can see here triple integral. So that's mean normally this will be deformed, that particular element will be deformed in the 3 dimension. So what you need to do to find out the total strain energy, so you need to integrate it. So that is the area under this curve. So under that curve, so normally we will consider only x directions. That's why we will get the one integral. So if it is xy both, should be double integral. So if x, y, z, so all whole 3 direction, we need to consider the triple integral. So in here dv means dx, dy, dz. So the limit of x here, okay, a to 0 to a. So this is 0 to b. This is y, dy. So first you need to integrate with respect to x, then integrate with respect to y, then with respect to z. So then you will get the total strain energy of the system. Okay. Is it clear for me and Shinna?
Yes.
Okay.
Yes.
So this is not the different thing, same thing, just introduce the integration. That's all. And these equations come up with the lecture note. I will move to the lecture note and I will explain the derivation. So just they explain in here the loading type, if it is axial, strain energy with the constant variable. This is the equation, and this is strain energy general term. So if it is not constant variable, so then you need to use this equation. But you have some kind of I mean doubt how it's proved, no? So we need to explain with the lecture note, because they didn't put that derivation part in the presentation. So I will move to the lecture slide, not I mean lecture note. Yeah, here. Yeah. So can you see my slide? I mean, my screen. Can you see, Shana, for me?
Yeah.
Yes, sir.
Okay.
Yeah.
So this is the we can express stress this way as well. The load divided by area, and this is the normal equation. F divided by A equals E times epsilon. I mean X divided by total length, kind of that equation. So you can rearrange this equation like this. Okay, this is, you can introduce here E and epsilon and rearrange that equation. So you can see deflections, I mean the strain equals P divided by AE, and this is a prismatic bar under tension. So this end is fixed. Okay, and when you apply the load, the linear pattern, deflection will be like this. Okay, so strain energy is equal half times sigma times epsilon. In here so we are not going to introduce in here kind of a integration, because we don't want to do the integration. We can do it simple manner, that's why. So sigma, it is equal P divided by A, let's see, and epsilon here we already read it down, and volume we know already, cross sections we know the length, so this is the total volume. We can substitute in here. So then when we cut off the A to this one, and P squared L divided by 2 AE. So this is the equations we saw in the if it is a constant variable. Okay, so if it is a constant variable, we don't want to apply the integration. Okay, so you can see this equation in the presentation, with the axial load. This is axial load. So with the axial load, this is the strain energy equation. Okay, so in the Castigliano theorem, we explain this one with a different way. So I will explain in here, but later on I will explain what is the Castigliano theorem. So if you know, if we now take the derivative for u, so this one we can get the derivative with respect to load, this P load. So you can see here. So the first derivative. So when you get it, what happened? 2P. So 2 will be cut off. So PL divided by EA. So P divided by EA, that is sigma, epsilon. You can see this epsilon. So you can see epsilon L. So epsilon L means initial length. Epsilon means strain. So normally epsilon equals extension divided by L. So this is the deflection. So in here they label as a displacement, not E, it is delta. Okay, so you can see this is delta. So when Castigliano theorem, they explain this thing. So what they explain, so if you want to deflection at any point, so what you need to do, you need to get the load at that point, and strain energy of the system, you need to differentiate with respect to that particular load, then you will get the displacement at that point. That is the Castigliano theorem. That is the only thing the Castigliano theorem. But there is an important thing. You need to select the, so normally you need to select the directions. So if you know that deflection downward, you need to select the force towards download. So when I explain the presentation, I told you there is a one title, so use dummy load. So normally we will introduce dummy load if it is if you want to find out the deflection at particular point. If there is no load available and towards that direction, you need to introduce dummy load towards that direction. Then you will find out using the dummy load, you can find out the deflection at that point. So that is the basically Castigliano theorem. Okay. So you can see the when so this is the P load toward this direction. At this point, deflection you can find out using this P load, the strain energy divided by delta, I mean dP. So this is a first derivative of the u, first derivative of u with respect to P. This is equal to delta O. This is extension. Okay, displacement. Is it clear? For me,
Yes.
any questions until this point?
No.
Pardon, I couldn't hear you.
No, sir, I understood.
Okay, Shana.
Okay, sir.
Okay, and so then there is another thing that you can see there towards to the axial directions. So this is assume this is x direction. So you can see cross section will vary. You can see in here cross section is constant. That is mean constant variable. The A, E, P is constant load, and initial length constant. The cross section also constant. This is constant variable thing. But in here, variable also not constant. I mean, sometimes you will feel like normally variable is not constant, but they just mentioned it's a variable means this equation governed by this variable. Okay, so those variable is constant. It has one constant value towards to this direction. It is not changed. But in here you can see towards this direction, cross section will be vary. So cross section has a function with the x direction, with the length, cross section will be vary. Can you see this equation? So when you substitute here L, so this will be 1, then cross section will be A. But if you substitute here 0, it will be 2A, 2 times in from here. So then the towards to this direction, cross section will be increased. So this is the cross sectional is a variable, but it is not the constant as well towards that direction. Are we clear about the constant variable and the general variable? Is it clear?
Yeah.
So you can
Yes,
see
sir.
same equation here. So we will use some equation like this, same equation, but with the integration, because the function a cross section is a function of x. Cross section not varied towards the y direction, no, is a direction, but only x direction it is varied. So what you need to do, you need to introduce that function. That's function. So same equation. So don't worry. So x, 1x will be cut off. Then you need to substitute the function of a with the x. So you can see here. So Virant, raise your hand. What is the problem?
Yes, sir. In the tension bar, the 2A mean the 2 times area, right?
Yeah.
The cross section area, no?
This is the area means cross section.
Okay.
So when you get the you are talking about the volume, I think 2 times. I think isn't it? The cross sectional area is 2
No,
times
sir.
in there.
Okay.
Are you clear about it?
Yes.
Okay.
So can you explain the equation 7?
Equation 7. This is given.
Yeah.
This is given. Don't worry about it. So this is given by that particular, if it is question, it will be provided. The how that variable will be vary with the distance or something like that. So it is a function. This is not a the standard thing. This is the, according to the question, it can be vary. Okay. So this is the function. The cross section toward this x direction, it is vary with the, you can see when you change the length of the bar, I mean, if you select this point somewhere here, okay, it is assume it is a half of this column. So it is L divided by 2. So this will be half. Okay. So this is this mean it is it will be 3a divided by 2, isn't it? So this is cross sectional area around this point. It is 3a divided by 2. When you substitute here L, the cross section, it will be give the somewhere here cross sectional area. Is it clear?
Yes, sir. I got the point.
Okay. So don't worry about this equation. So normally, if it is vary, they should provide the variation, or they will provide some clue to find out the function. Okay. So they will give some hint. So don't worry, if they didn't provide the equation directly, definitely they should give the hint or some kind of clue. Okay, this is the way you need to find out the function of that particular variable. Okay, so then so you can see there is a P and elastic modulus load. So those things are constant. So you can substitute to function of AX. So in here, capital A within bracket, these are the things where only X is a variable. You can take A as A is a constant. Okay, so I mean in this function A is a constant. This is a kind of constant thing. So you can take it out as well. So you can see from the integral, you know this one from advanced level. So you can take out constant things from the integral, take it out. So p squared L divided by 2ae. Those things are constant, and these are the things as a variable. But L also constant, but you can't take it out because it is combined with the x as a minus x. You can't take it out. So you need to integrate this one with respect to x. So you know the 1 upon x, it is ln x, okay, or log x. So in here they introduce the log with the integration. So I am not going to explain the integration part. I hope all of you have knowledge about the integration and differentiation. Okay, you should have that one. If you have any questions with the integration and differentiation equations, so you can ask from it, but I'm not going to explain. So this is integrations of this function. So introduce a limit, and so when upper limit and lower limit, so you can introduce the upper limit first and minus lower limit. So 2l minus l, that is l log l, and then 0, this is minus 2l. So then log, I mean, this is minus, so it minus times minus means plus log 2l divided by log l, because the log rules, if it has a minus, you can take put as a fraction. So this is kind of integration. Okay, don't worry, integration and mathematics. There is no any kind of theory, new theory. Is it clear, everyone? So that's how it takes a log 2. Otherwise, I can write down here. So I will just show in here. I'm sorry, it's loading. I'm sorry. You can see my screen, no? Shanal, someone can you tell me?
Yes,
I
we
can
can.
see.
You can see. Oh my. So, but I can't. Okay, can you see where I stood? Somewhere here. That equation, can you see? Because my computer display was stuck. That's why I'm asking. If you can't tell me, if you can't see, or can see.
Yeah.
Okay. So in here, so I will write down here. This is log the minus L after substituting this upper limit, and minus this minus, and the minus minus it will be plus log 2L with the 0 2L. So this is plus, so the this one should be divided by this one. This is minus. So log 2L divided by log L, 2L divided by L, it will be cut off to L, and this will remain only 2. Are we clear? So that's how we can deal with the integration. So you can see here, but we had the limit in here, but if you don't have limit, so you need to use the integrations, and you can see I will show you again presentation, and the presentation, this is the variable is this is general format. So variable, if it is constant, you need to use this equation, this kind of equation. And so I will explain other part as well. So if it is uh, those things valid for the axial load, if it is a torsion, so the strain energy equation similar manner you can find out. So this is the equation. It is like this. Okay, so you can deal with like this and end up with somewhere like here. Okay, so just believe me now, if you can deal with that equation later at the home. So this is the equation. T is the torque, and G is shear modulus, like elastic modulus. This is polar moments, and the initial length, like that. So as I told you, if you want to find out the deflections, or in here the torsion, there is no deflection. It is a kind of twist. Okay, twist angle you can find out using the torque. You can differentiate with respect to torque, that is strain energy. You can uh, differentiate with respect to torque, and you will get the, so if you differentiate this one, 2t, so 2 will be cut off. So TL divided by G J. So TGJ means it is belong to like this manner. Strain, shear strain, normally we will call as a gamma, like this. So this is gamma L. Gamma L means theta. Okay. Normally shear strain we call like this. Shear strain theta divided by, okay, it cannot be L, but like this. Okay, gamma L, it will be theta. So this is strain, twist angle. This is shear strain. So if it is a bending moment, so this is the torsion. So if it is a not constant variables, if it is general manner, you need to introduce again like this integration. Assume if it is load is not the constant thing, so you need to introduce that function with the integration. That is the thing you need to know. And this is the functions with the bending moment, and this is the distance, and this is the second moment of inertia. Then the stress, So this is the, in here you need to keep in mind there is a sign convention. So I will explain that sign convention later, but the bending moment functions you can introduce to that particular functions what you learned early. So you had that equation in here. So if you remember that equation I explained earlier, sigma squared divided by 2e. So in this equation you can introduce this you can substitute this my divided by I. So you can see here m squared, y squared, and I squared, and 2e, you can see. So then dx by dx dA means, this dA means dy dz. Okay, this is cross section. If you get the particular bar, this is, if it is x direction, this is dx dy, this cross section. Okay, that's why dA. So dA dx. So you know in I think in your A level or in your mathematics in your university you learn some theory like second moment of inertia is equal to y square dA if it is Iyy. If you remember this equation, so in here you can see that part, integrations y squared dA. So you can put you can substitute that to that part equal as a I. So if you introduce that I in here, what happened? One I squared, from I squared, one I will be cut off, and this is the remaining part. So later on we will use this. There is a triple integral, okay? Triple or double integral. There is a dx dA. So one integral will be gone out, because with the dA, you can see here there is a with the dx there is integration. Okay? Don't worry, otherwise you will think there is a one integral. So if you introduce I here, there should be there shouldn't be another integral or something like that, but it should be, because there is a dx. Okay, dx dA, this should be double integral. So one integral will be gone, but there is a remain another integral with the dx. So later on we will use this equation, because normally we can easily find out second moment of inertia, sorry, bending moment and other things. So you can see in here the, because these things they are not going to explain, just give the lecture note and you need to read and understand. I just used this lecture note and I will explain how to derive that equation. Okay, you can see the presentation, they just tabulate that particular equations, and you need to use that equation. I will explain here. So you know bending moments around this point px, this is distance. So around this point means, if it is distance xc until this point, this is px. If they are somewhere here, you need to multiply by that length. So you can introduce that px in here, okay, if you want, and you can again find out that particular equation, same equation. And yeah, we can see here they introduce px, and then integration 0 to L, here to here, 0 to L, and then x squared is the these things are constant. So s squared, when you integrate, it is s cubed divided by 3. So that's why in here 6, 2 times 3, ei p square L cube when you do the limit. Okay, and then you need to differentiate with respect to p to find out the deflection at this point, because normally you can see in here p will be downwards. Definitely this beam will be deflected downwards. So you don't want to introduce another load here, there is a load. So when you differentiate with respect to P, you will get the deflection at this point. So when you differentiate with respect to P, those things are constant, you can take it out. And P squared, it will be P 2P. So from 6, it will be 2 times 3, so 3 will be remain. So this is the thing. This equation equal to delta, if you remember earlier we discussed. Earlier. So this equation equal to delta, you can easily find out this loading system also. We can use this system also, you can use Castigliano theorem, because the theory we will use, it is valid for this one as well. So this is the table you can see in the presentation. I will move to the presentation. You can see here with axial load, the strain energy constant with the constant variable. We already derived this equation. And if it is a general term, I mean, general term means you can use that this equation to here as well. Then there is no limit. These are constant. So general thing. And bending condition. So this is the equation. So the constant, if it is constant, this is the case. If it's a constant variable, if it is a general case, the bending moment will be vary along the length. So normally that is the case. Bending moment not the constant along the length normally. So this is not the general case. This is a constant variable thing. The torsion, this is the constant variable thing, but it is also sometimes not the constant along the angle. So around the angle you need to consider along the distance or around the angles, it will be vary. So you need to focus on that, on that as well, the general manner there. So this is the table. So I will move to the presentation again. Can you see my presentation slide? Excuse me, are you there?
You can see the tables. Yeah, presentation slide.
Presentation slide you can see, no?
Yeah.
Okay. So same table here you can see. So they just move from after this slide, they just move to this slide. Okay. So I until that point I explained using that lecture note. So now you have rough idea. So how to find out the strain energy equations? So that is very important. The different loading condition, you need to know how to find out the strain energy, because we will use in the Castigliano theorem. Strain energy is the main uh, concern to find out the deflection using Castigliano theorem. So you can see with axial load, how to find out the strain energy, bending load, how to find out the strain energy, torsion, how to find out the strain energy. So this is only for the strain energy. So let's see how we can use those strain energy theory to find out the deflection. So you already know now, but as a theory, still you don't know. So I will explain the Castigliano theorem now. The Castigliano theorem, so for any elastic system which obey the superposition principle. So what is the meaning of superposition principle? So you already know that one, as I'm asking. Superposition principle. Did you ever heard that word, superposition principle? Don't tell no. You should. Someone?
So the net effect can be found by the sum of individual,
Yes, that's
like,
the theory. Yeah. So you
yeah.
can find out the net effect, the resultant effect with this calculation. The each individual thing separately. You can calculate the individual things separately. That means those individual things should be independent. Those are, if it is dependent, you can't calculate those things separately, because the one assume there is a 3 load. The 2 loads are independent, but other one will be depend on that 2. Then you can't use superposition principle. So that means that those loading condition and other things should be independent. Then that's the meaning of superposition principle you can apply. For an elastic system which obey the superposition principle, the partial derivative of the strain energy. So you already know how to find the strain energy now with any kind of loading condition. So that strain energy equation, you need to partially find out the partial derivative with respect to the force. Okay. At any to any force, give the corresponding component of the displacement for point of application. So where you need to find out the deflection, you need to apply the force. Normally, if there is no load, you need to apply the dummy load. Okay. So in the first few cases, we are not going to use dummy load, because they will ask from your questions, and in this presentation also they will use the deflect. They will use to find out the where the load available. But the next stage, they will ask the deflection. Some point there is no any loads. So then you need to use dummy load. Okay. The point of application of that force in the direction of that force. So if you have the load at that point towards the upward, if there is deflection downward, so you can't use that particular load towards the upward. So you need to introduce dummy load towards the downward. Hope you understand that. So this is the Castigliano theorem for an elastic system which obey the superposition principle. So you don't want to keep it mind this word word by word to get the idea. The elastic system means it is obey with the linear region. Okay, that means the sigma equals E epsilon. That equation will be obeyed. For an elastic system which obey the superposition principle, the partial derivative of the strain energy with respect to any force give the corresponding component of displacement for the point of application of that force in the direction of the force. So that is the Castigliano theorem. They will not ask this theory as the word, but they will ask that theory with, in that question. So you need, if you understand the theory very well, you can use that theory in the questions without any problem. So the force may be couple of moment. Yeah, these are some kind of conditions. Okay, only statical independent force are being considered. I already told you, because otherwise you can't apply the superposition principle. So only statically independent forces are being considered. That is, it can be added and subtract from independently of any other force in the system. And non-independent thing, you can't use this theory. So an example of a non-independent force is the reaction force supporting beam, as you would not be able to remove the reactions force without alternating at least one other force. That means, so you can see due to this, the weight on this beam, so the supported point, there is a reactions. So those are independent, not independent. These are independent. Okay. Due to this load, this reaction will be varied. So you can't remove this load because it will happen due to this load. So these, just for understanding, these are the dependent force. This is independent, because if you vary this, okay, you can't remove if you want. You can add more if you want, but in here you can't do anything, because if you change here, it will change. Okay. Leibniz rule. So you should know these rules to do when you do the calculation. It will be very easy. Without this rule also you can do that one, but it will be very difficult to do the calculation. The Leibniz rules means kind of the chains. I think you know the chains rule. So like that rule. So normally we will differentiate with respect to load. This is the P, the strain energy. When you differentiate with respect to P, so this is the equation with the bending moment of, if you remember, strain energy general equation. So you can see in here, you need to do, first thing is you need to do the differentiation. Then you need to do the, sorry, you need to first, you need to do the integration. Then you do the differentiation. This is the thing you need first thing. This is first thing. You need to integrate first. Then you need to differentiate. But because U is the, this is U. This part is U. U divided by dp, du divided by dp. But in the Leibniz rule, you can see here, what you can do, you can put the differentiate part inside and take it out, integrations. You can see here, you can take into this d divided by dp. So what you need to do, you need to differentiate with respect to p, this part first, then integration with respect to ds. So this is mathematics rule. So you can these two equal. That means after integration you can do the differentiation, or else you can differentiate and then you can integrate. You will get the same mass. Okay. So in this lesson, if you integrate and then differentiate, it will be little bit difficult to do the calculation. So what you need to do, you need to differentiate then integrate later. So that's why Leibniz rules we will use. Normally this is the equation you will get. Then you need to rearrange it using Leibniz rule. So what you can do after finding this equation, so using Leibniz rule, you can rearrange this one. Within bracket you can put the from Leibniz rule. This is the rearrangement. Otherwise you don't want to any other things, explain the theory part and other things, Leibniz rule theory and other things you don't want to prove. Just you can mention this is from Leibniz rule. You can turn this format from this format. Are we clear about that? Yeah. Then you can see here. So if you the bending moment, definitely there is a kind of P, I mean load. Bending moment normally we will calculate with the load. Even though there is a M, you can't see there is a P terms. But okay, assume this is a linear force, just for understanding, Px. Okay, so then there is a P. So when you differentiate with respect to P, so there is a P. Okay, the E and I doesn't have P. Only bending moment has a P. So when you differentiate with respect to P, so what you need to do, M should be differentiate with respect to P. So this M squared will be 2M. So you know chain rule. So if we have M differentiate with respect to P, normally what we will do, M, this is chain rule, okay, dm by dp. So this is the thing. If it is M squared, this will be 2M. You can see in here, 2 will be cut off, 2M. and dm by dp. So when you m, if you differentiate with respect to b, this is the thing you need to do. Chain rule. This is called chain rule. So after Leibniz rule, they introduce the chain rule. Then integrations m dm by dp dx. Ei is the constant thing, so you can take it out. M you can't take it out because it is dependent on the length. I mean x. This is a function of x. This is a function of p and x. Okay. So when you differentiate with respect to p, you don't want to revert the x, only p. And then after differentiate this one, you can substitute here and simplify this function and integrate with respect to x. That's the thing you need to do. And in here we will do the calculation kind of format. Okay, so you should have the steps. If you follow these steps, it will be very easy. Normally, what you need to do, you need to find out the bending moment first. Then you can substitute here bending moment without any problem. And then you need to find out the first derivative with respect to p, that load, particular load. So if you want to find out the deflection at any point, you need to use that load and differentiate that bending moment with respect to that load. So it is dm by dp, and find out separately that first derivative. Then use that equation, substitute here m and that first derivative, and then integration and do the calculation. You can see during the examples when I explain during example explanation, you can easily understand what happened and how we can do the. You can follow how we can follow that steps. If you follow that step, you can easily do the calculation. You can easily understand. But if you don't want to follow that step, you can also you can do the calculation, but it will not too much easy if you don't understand. If you understand, it doesn't matter. But until you get the idea behind this, I think it's better if you follow these steps. So let's see with this example. It's available in your lecture note as well. The cantilever beam subjected to distribute load, and you can see distribute load. This is distribute load. This is kind of distributed load. At this point, there is a P load, and in here distribution load is 0, but here it is Q node. So distribution load function is Q, so you need to find out the function of this Q. Okay. So if it is 0 here, if it is Q node here, you can find out with the length, it will be vary. Okay. So subject distribution load and point load. This is point load, is shown in figure 9. Apply Castigliano theorem to determine the vertical deflection delta B at B. So you can see normally if load is available in this direction, deflection will be happen this direction. You don't worry about the using dummy load or something. So this is point B. There is a point load. Without any problem, you can do the calculations using this P load. Consider only the strain energy of bending. The flexural rigidity is EI. So normally we call EI, E times I is a flexural rigidity of material. It is the material constant. It will be vary with the cross section, but we call it flexural rigidity, EI. EI is the constant thing. Normally, if they provide the flexural rigidity equals some value, you can substitute that EI value in here. Okay. Then this is the condition. So, but you need to know sign convention. So this is kind of sign convention. So normally we will not consider whole beam. Yeah. So whole beam we are not consider. We will consider part of this beam, and we will derive the equation for that part of the beam like that. So when you separate somewhere here, virtually you will separate in this somewhere here or somewhere here. So then you need to find out the bending moment from this point. So until at this point, what is the bending moment? And due to this distribution load, what is the bending moment around this point? Like that, you need to find out. So when you virtually divide to two parts this beam, because I hope you know what is the reason for that. So because if you use bending moment this point, you don't have the variable, because you will get the L length, that is upper limit of this expansion, the length function 0 to L. If you use upper limit, you don't have the integration. So if you get the function of x, this from this point to this point, function x, that means length vary. So you should have the, in the equation you should have the x. So then you can do the integration with respect to x, so with respect to y or something like that. So if you use this particular point, this is upper boundary, this is lower boundary, this is x equals 0, this is x equal L. But you need to use intermediate point, then you can do the integration without any problem. Okay. When you do the calculation, you can easily understand what I'm explaining here. So sign conventions, if you separate, so that's why we need to sign convention. So if you virtually divide this one, so due to this payload, this will be bending like this. So you know bending, if it is like this, you call it sagging and hogging. I hope you understand this theory in the your last year. I didn't know the module name, but you learn these things, bending moment and other things, the civil module, civil modules. So common subject there also with civil students and mechanical students. So this is called sagging. The minus. Normally, if it is loading as like this, is a minus. If it is a bending like this, because it's a hogging, so it's a positive. This is shear force sign convention. You can see if it is like this, downward and upward, this is positive. If it is like this, it is negative. And if both shear force and bending moment together, so this is hogging and this is same thing, the positive. If it is a sagging and this kind of shear force, it is negative. So this is the separation. So the one particular column, if you separate two virtual columns, you can see this is a cross sections. So this side it will be downward, this will be upward. So we call this is positive. If it is left side one is upward, right side one downward, it is shear, shear minus shear. And this kind of separation, it is positive bending moment. This kind of separation is negative bending moment. So this is kind of sign convention. You should know this thing, sign convention, other things. I just remind this one. So example one, we will discuss with this theory. So first we need to determine the moment at any given distance. I told you, because otherwise we don't have function. So this is the point we select, x distance. Okay, so x can be vary 0 to L. Okay. Then, so we will consider this part only, derive the equations, because we don't want to worry about this side. X when it's L, normally at this point also represent. We don't want to worry about this side then. X is 0, it will represent this point. So we will consider only that x length. So P. So due to this P, around this point, bending moment is Px. Okay, but it is minus Px. So because this is sagging, it will bend to downward. Okay, minus you, because you need to consider the sign convention. I told you. So minus Px. So due to this point load around this point. Then distribution load. So selected point and from the point P to selected point. So this is the distribution load. So you need to find out the load at this point due to this distribution load. So how we can do that? We know the load Q naught at the L length. This is 0. So you know the gradient. Q naught divided by L. This is kind of y equals mx type one. So what you need to do, this is the gradient, this is x. So if it is x0, q naught q will be 0. This is the function of this curve. So if it's x0, this will be 0. If it is x equal L will be cut off, then q naught. When length of x equal L, that distribution load will be q naught. So the figure 9, you can see that one. So this is the function. So at this point, load q naught divided by L times x. Okay, so then if you have distribution load, so you can't find out the bending moment. It is very difficult. So you need to find out the equivalent point load for that distribution load. So normally equivalent load will be applied on the centroid of the distribution load. If it is a triangle, this is triangle. So if it is triangle, you need to know how to find the centroid. If it's a square shape, you need to know how to find the centroid. If it is a circle, you know what is the centroid. If it is a different shape of distribution load can be there, rectangle. So different kind of distribution load has a different centroid. So if it is triangle, so you know the distance to the triangle from this side and this side, and if you want this side as well. So I mean this corner. So from this corner to centroid, this is centroid. So x upon 3. From this side, it is x 2x divided by 3. Okay. So this is trigonometry, not this subjecting. So how triangles centroid, how to find out. So this is x upon 3. Then when you do the some example and tutorial, you will see there is no the complex shape of the distribution load, only triangle and rectangles and square shape kind of distribution load. You don't worry too much. So if you know the, so if you don't remember, when you do the calculation, few tutorials questions, deal with the questions, you will easily grab okay how to find out the centroid. So if it is triangle, so from this corner to this point, the horizontal distance is upon 3. Okay. So now we can find out the equivalent point load for this load. I mean this distribution load, all distribution load. So total load you need to find out of this particular part. So this is q naught x time x divided by L. This is 0. So this distance x. So what you need to do? Find out the area of this triangle. This is the total load. This length we know, this length we know. Then you need to multiply by half. Half multiplied by this one and multiplied by this one. So you can see the total load of this distribution load. Okay. If it is the L, you can see when you can substitute L will be cut off in here L. In total load, Q naught L divided by 2. Yeah, that's true. If you go to the first figure, you can see that is the total load of the distribution load. So this part of column, this is total load. It will apply as equivalent point load will be applied from this corner to, x upon 3 distance. Okay. So this is equivalent. These two equal. Now we know the equivalent point load. Now you can find out the bending moment around this point due to this distribution load. So this load multiplied by this one. So it will be, it is also sagging. So it is minus So when you multiply by this one, q naught x cube, because there is x, there is x, there is x. So x cube 12 times 3, 6, 7. So this is the bending moment. Bending moment at this point. So now we know the total bending moment with the summation. As I told you, this is the first step. You need to find out the bending moment in one particular point. Okay. So then, yeah, Virant, you can ask. I saw someone raise your hand. I think it's Virant. So what's the problem? I can't hear you. I think you mute your mic.
Sorry.
Oh, yeah.
So in the previous slide,
Yeah, in here.
yeah, the half into q naught x over L into x.
Yeah.
What is the equation? Is it a force or?
Pardon, I couldn't hear you properly. At the last sentence, what did you say?
Is the equation the equation is equal to force or what?
Equal
Not the red
to
color one.
this equation.
Yeah.
This is total load carry on in this with this distribution load as an equivalent 1 point load. This is the 1 point load. So this is represent total load carry on in distribution load in here. So if you know the area of this distribution load, so that is the total load. Are we clear? So this is the point load. I mean, this from distribution load. This at this point, this is the load. At this point, it is 0. So you know how to find out the area of the triangle. So this is length. This is the length. This is this length. So you know this length and this length. Then you can multiply by those two and multiply by half. This is the area of this triangle that is represent the total load carry on this column. Are we clear? Hello, I can't hear you. I couldn't.
Yes, sir. I got the point.
Got the point, no? Okay.
Okay. Thank you.
Then, so as I told you, you can find out the total bending moment, the selected point, then first derivative. I told you. But you need to think about this load, this point load in here. We need to deflection at this point, no? So you need to consider this point load. The Castigliano theorem explained, if you want to deflection some point, you need to use at that point load towards to that particular direction, required direction. So already there is a downward, the load point load apply on the downward. So no worries, you can use that P load. So that's why they use that P load, okay, dP. So dmx bending moment, you need to differentiate with respect to P. So you can, when you differentiate with respect to P, what happened? There is only P available in here. You don't want to do about this distribution load. There is no P. So this is kind of constant. Okay. So when you differentiate with respect to P, this will be -1. Then -1 time x, it is minus x. X like a constant in here, because that's why we call it a partial differentiation. So x is a variable, but when you differentiate with respect to P, it's like a constant. So if you differentiate with respect to s, it will be minus P. But it is minus it. I think you know the partial differentiation as well in the mathematics. You already know that things. So this is the first derivative of bending moment with respect to P. I hope it's clear. Now we will use that equations to find out the deflections. We need to find out the vertical deflection at point B. So that's why delta VB. So this is vertical deflection at the point B. That's the meaning of VB equal strain energy we need to differentiate with respect to P. That is the theory. So that is the Castigliano theorem explain, and it should be equal to this equation. This is the Castigliano theorem explain later on. We modify that one. So d divided by dp. This is u. This is u. I already explained this one. Strain energy due to bending moment. Okay. So then we will use Leibniz rule. So we will interchange integration and differentiation. You can put inside to the differentiate part. But differentiate part also you can, using chain rule, you can rearrange like this. Okay. We already discussed this one. This is the finalized equation we I show you in the last I mean 4 slides earlier. So this is the equation. So now what we can do, substitute here bending moment. We already find out the bending moment equation, and we already know the first derivative of bending moment with respect to P. So now we can substitute. This is the bending moment equation. This is the first derivative with respect to P. And limit 0 to L. X can be weight 0 to L. So then differentiate. Already differentiate, so you can integrate it. So you can expand this one. So minus and minus, it will be plus px squared, and this will be also plus q naught s to the power 4 divided by 6l, and then you can integrate this one. So when you integrate this s squared, it will be s cube divided by 3, and this one it will be s to the power 5 divided by 5. Then introduce limit L cube and L fifth, and likewise the other part will be 0 because it is 0. Then this is simplified like this manner. So this is the vertical deflection at point B. So if you want to find out as a number, you can substitute P load value, Q naught value, L values, E I value, already it will provide. So then you will get that as a number. But if it is as a symbol, if you want to keep it, so this is the answer for the vertical deflection. Are we clear until that point? So I explain this particular one first examples very slowly and I mean very explainable manner, because if you don't understand, you can't easily grab other things. Okay, are we clear? Any questions? If you have any question, you can I will give few seconds. Raise your hand. I will give the answers for that your questions. Any questions? Okay, I will move then. Use of dummy load. I told you where you should know where you should use to dummy load. Okay, so don't use if it is unnecessary. So if it is only necessary, you should use dummy load. If the deflection is required either at a point where there is no unique point load, as I told you, if you want to find out deflection one particular, assume the first example we discussed the deflection at point B. So if there is no any point load like P load, only distribution load available, you need to use dummy load. Definitely, there was point load. That's why you didn't use the dummy load. Okay, so, is no unique point load or in a direction not aligned with the applied load. So if it is deflection downward, if you have point load upward, that is also not good. That is also not useful. So you need to use dummy load to downward, because due to, even though there is a applied point load at that point upward, due to resultant force, that particular point will be downward. Then you need to use dummy load. Okay. With the applied load, a dummy load is introduced at the desired point acting on proper direction. So that's the way. The deflection is obtained by first differentiating the strain energy with respect to dummy load and then taking limit as the dummy load approach zero. So dummy load means actually it is not available, but you will just use as a, that's the meaning of dummy. Okay, so you will use dummy load to find out the first derivative with respect to dummy load. Then you need to put as a dummy load equals zero. Yeah. So with the sentence you will easily not grab, but when we do deal with the question, you will easily grab what I explained in here. Okay. Okay. When to put q equals, don't put q equals 0 at the very beginning. Then it's not useful. Normally q is dummy load, the symbol of dummy load, capital Q. Yeah, that is where, yeah, as I told you, after we find the first derivative of m, first derivative of bending moment, we can put the dummy load as equals 0. It will not affect then final result, but without finding first derivative with respect to that dummy load, don't put as q equals 0. Then it's not useful to put in the dummy load as q, because your purpose is gone there. So with this example, you will easily understand how we can find out the deflections where there are no any point load at that point. So same question, you can see same thing, same figure. I'm not going to read, but you need to consider the midpoint. That means the point C, they didn't mention in here point C, somewhere here, point C, at the midpoint deflection. That means delta VC, okay? Vertical deflection at this particular, okay, somewhere here, okay? And they mention in here, consider only strain energy of bending, okay? You don't want to consider the axial or something like that, only strain. If it is axial also available, you need to separately calculate the axial as well. That's why superposition principle there. And if there is a torsion, you need to separately calculate the torsion deflections, then combine together, okay? Consider only strain and energy of bending. The friction rigidity is EI, same beam, same values. So you need to find out the point C somewhere here. Then yeah, so this is the thing. At the point C somewhere here, there is no any point load. You need to introduce dummy load like this, and you need to select the, I mean you need to separate the this column to derive the equation somewhere here. But after, when you select somewhere here, you will get the equation without q. You can see, because q will not affect to the bending moment from this point, okay? So you will consider this part. If you consider this part only, q is not affected. So you need to derive the equation to this part and this part separately. That means s equal 0 to x and x to L separately you need to derive equations. Okay, you will see. Yeah. So XL means x in here center point. So until center point, 0 to x means 0 to C, at the C point, it is x equal L upon 2. So this is the one of range. So we already did this equation. I'm not going to again explain that one. Same diagram. No? So then L upon 2, that center point to the fixed point. So L upon 2 to L. So same thing. This will affect definitely because without any problem. But this one, additional thing, the point load. So if you consider somewhere here, if you divide this beam somewhere here as well, sorry, somewhere here. So this length and this is also second. So minus q. This is not, we cannot get as a x. Okay, this is not x. From here it will count as x. So L minus x you can get. In here x minus L L2.
Excuse me, sir.
Yes.
For that, from where did we take x for the second part?
Second part means Q for Q.
Yeah, with the point load. From where to where did we take the x length?
Pardon, I couldn't understand what is your question.
For with the point load when
Okay,
we
I
are
will show you
considering
the
the
figure.
moment.
Okay, can you explain with this?
Yeah, when we are taking the moment for the distance L over 2 to L. Where did
Somewhere here to here.
Yeah.
Okay.
So, which now when we are taking x minus L over 2 when we are taking the first derivative, which is in the next slide.
Okay, I understand. Okay, I will explain, and if you don't understand until that point, okay, tell me. Okay, so assume somewhere here. Okay.
Yeah.
So this is x, isn't it?
Mm.
And this length we already know until Q point. At the C point, Q load, it is L upon 2. Am I right?
Yeah.
Okay. So this length, then automatically we know x minus L divided by 2.
Okay. Okay. So
Okay.
got it. Yeah.
So you can see the bending moment. So take general point. When you calculate the bending moment, get the general point. Okay. Don't take upper boundary or lower boundary, something like that. So don't calculate the midpoint bending moment at the C point. Then you will again eliminate the Q. So we should have Q as well to find out the deflection. You can see here Q is available. Now what you need to do, you need to find out the first derivative with respect to Q. Let's see what happened. First derivative with respect to, because we don't do the differentiation with the P. P is belong to B point B. So you are going to find out the deflection at the point C. So then you need to use dummy load Q. So that is the Castigliano theorem. So dm by dq, it is equal 0 this part. That means it will not affect to 0 to L upon 2 part. Because dummy load not affect to the point C is available after L upon 2. So then L upon 2 to L region, this part will be 0. There is a Q. So it is equal 1, then this part only. Differentiation, that's just differentiation, minus x minus L upon 2. This is the first derivative. Okay. Then we can put as a q equals 0. After derive this equation, bending moment first derivative, you can put as a q equals 0. Then this is same equation because there is no q. Q we just put ourselves, and it is 0 also. So you can see there is no q now. So now we have first derivative with the q as well, even though there is no q. Okay? So q equals 0, then this is the bending moment equation. So you can substitute bending moment equation this one, and dm by dq this one. You can see now this is the equation. Now we can find out you can read this one, I already explained this one. So then du by dq, that is the point C vertical deflection. So this is the equation with the u, introducing u here. Then rearrange with the Leibniz rule and chain rule. Then introduce and substitute here bending moment equation. This is bending moment equation. This is the first derivative with respect to q. Then expand it and just integrations. I'm not going to explain this one. Integrations and substituting limit. So you will end up like this equation. Okay. So now you know how to deal with the dummy load as well. If you don't have point load towards to required directions, you need to use dummy load. Keep it in mind. So until this point, do you have any questions? If you have any questions, you can raise your hand.
Sir, always do we make the dummy load equal to 0 after integrating, or
Not after
is
integrating, after differentiation.
sorry, yeah, after differentiate?
Yes, of course. You
Is
should.
that the case every time?
Yes, dummy load is it is not a actual thing. No? You are just used to find out the differential equation. I mean, first derivative using that one. So q is doesn't have value. It doesn't have value.
Yeah.
Okay.
Okay, sir.
Then with this example, I will explain the. You can see in here there is no point load. Then the first example we have at least p load somewhere, p1 point load somewhere. In here only distribution load. The A to B, the distribution load is available, and the shape of the distribution load is a rectangle. So total load of the distribution load is q times x. Okay, qx, this distance by this length, so qx. A simply support beam AB subject to distributed load is shown in figure 13. Okay, the load intensity is q. Apply Castigliano theorems to determine the vertical reflections at the midpoint. That means somewhere here you can see there is no point load, then you definitely need to introduce the dummy load. Consider deflection due to bending only. So if it doesn't mention like this, you need to consider other thing as well. Okay, if there is available that some other things. Okay. The fractional rigidity is EI. So let's see how we can deal with this kind of question. So you don't have dummy load in here. I mean point load. So you need to introduce the point load downward definitely, because it will deflect. You can see we have general knowledge. It will deflect like this. So downwards point load at the point C. You need to dummy load. You need to introduce. Yes. Okay. Very important thing I couldn't mention in here. So you don't want to worry about the whole section. So if you consider whole section, no worries. Okay. So this is kind of shortcut. So don't apply this theory for everything. In this beam, it is homogeneous. I mean homogeneous and symmetric around this center point, midpoint. So this side and this side. So you can consider half of this beam to do the calculations and multiply by 2 for the whole section. So that's why because of symmetry, only half of the beam need to be considered. This is kind of special cases. So if it is symmetry, you can consider the half of the thing and then multiply by 2, you will get the if it is symmetry 3, then you can multiply 3 like that. So it is kind of shortest method, but it is special case. Keep it in mind. Don't use everything for this one. There is no point load at the midpoint, thus dummy load Q is introduced. The reaction force point B. Reaction force then you need to find out with the dummy load. So because if you consider the half of this beam, then somewhere here to here, then dummy load will not account to a equation. So you need to find out the reaction. Okay. So if it is a Q, Qx, this Qx divided by 2, this is Qx divided by 2, the half of, and this is Q divided by 2 and Q divided by 2. That is the reaction. Q, this is x mean L, no? Total length L, so QL divided by 2. So I think it's clear. The reactions at point A and B, the same values. Now the reaction is dependent on both Q, capital Q and simple Q. That is very clear, no? So those are not independent, it is dependent. So this is the case, okay? So we will consider this half only. So this is the reactions. So when you consider this half, we will consider somewhere here point. some point, general point. So if it is rectangle, I told you this is a half length to centroid. So you already know the point load directions downward. You don't want to worry about. But when you consider in the general case, Q will be eliminated because somewhere here you will consider. But Q is somewhere here. You don't worry about that. So it is upward Q divided by 2 plus QL, simple QL divided by 2. This is the reactions. And you need to find out the equivalent point load for this distribution load. This is QX total load, and you need to multiply by this distance. This is the centroid distance. So bending moment around this point and bending moment around this point due to this load, need to separately calculate and get the summation. And important thing, this is due to this load, this equivalent the point load, it is minus, this is positive, this is upward, so it is hogging, this is sagging. Okay, you can see this anti-clockwise direction is positive. This is the reaction due to point B reactions bending moment. This is clockwise directions, so sagging, so minus QX square divided by 2. Okay, here QX total load applied, this is QX square divided by 2. I hope it is it's understand. Then get the summation. This is the bending moment equation. Now what you need to do, you can find out the first derivative with respect to Q, dm by dq. So there is no any capital Q terms. There is no any capital Q terms. So in here only capital Q, it is x divided by 2. Now use the equation. In here you can see multiply by 2 here because we consider only half of the sections. Okay. So if you consider the whole section, you don't want to use 2 here. So you can see limit 0 to L upon 2. That means half of the beam. That's this is because this is symmetric column. That's why. So du by dq, and this is, I think I don't want to explain again now. So this is very important thing in here. This one, half of beam we consider. So that's why we will multiply by 2. And then substitute here m. We already know the function of m. And dm by dq. This is point C. This is represent point C. Then expand it and integrate and substitute the limit and other things. So if you want to put the q equals 0, you can put after q equals 0. Then otherwise you can put the q equals 0 somewhere here as well before substituting here. No worries. So you will get the same answer. So after finding also you can put as q equals 0. No worries. After finding bending first derivative with respect to q, you can put the q equals 0. This is 0. So q terms will be eliminated. Here also there's a thing happen. So are we clear about that? Any questions? Are you there? I don't know. Or if you leave, I don't know.
Yes, understood.
Okay. Example 5. There is so many example in your the lecture note, and tutorial also have good question. So you will get the question. Maybe sometime you can get at the exam you can get the curve beam with the distribution load. Okay. So that is the worst case you can get at the exam. It's very difficult to do if you don't understand the theory part. Otherwise, it's very easy.
The last time deferred exam, we got
like that
curve beam with the distribution.
Yeah, that is the worst case you can take. So if you understand that theory very well, you can easily do the calculation. But if you don't understand, you are in trouble, because the distribution load and if it is a curve beam also, then you will be confused.
Yeah.
That's the thing. Okay. Okay, I will separately explain this one. This is only curve beam with the point load. There is no any point distribution load. A thin cantilever ring, cantilever in that, because this is fixed end. AB having a circular axis of the mean radius r. You can see this is the center of this arc. Is built in at B, at carries a vertical load P at its free end. Okay, point A. Shown in figure 15, apply Castigliano's theorem to find vertical reflections at point A. Then you don't want to introduce the dummy load, because there is a point load. Consider only the strain energy of bending. The fracture rigidity is EI. Okay, so in this case, you need to use the angle, theta angle, for your calculations. Instead, the length x, you will normally use in x, but in here you need to use the angle. Okay, this is kind of curve beam. So let's see how we can deal with this one. So get the general point of this arc. Okay, so assume this is the general point. So bending moment around this point due to this P load, there is a distance. You can easily find out horizontal distance. This is arc radius r. This is theta. Then it is sine theta, r sine theta. This length is r sine theta. This length is r cos theta. So this is the bending moment. Earlier it was a function of x distance. This is function of theta. Okay, bending moment around this point P, this point load, r sine theta, this distance. And then first derivative with respect to P, because we need to find out the deflection point A. That's why there's a P point load. So find out the first derivative r sine theta. P equals, when you differentiate with respect to P, it is 1, r sine theta. Now we know the terms. So in here they didn't mention about the calculation, other calculations. Then use the deflections, delta equals 1 upon EI integrations, that function, this equation, this kind of equation you can use and do the calculation. But this is very important thing. Find out the bending moment and first derivative. In here, very difficult if you don't understand. If you introduce the distribution load somewhere here until somewhere here, so you need to find out the equivalent load, point load for that distribution load as well. Because then it's arc length. You know how to find the arc length, r theta, like that. So you can find out total length and find out the centroid point, and then find out the bending moment. That's all you need to do. Statically determinate structures. Yeah, remove redundant supports to make the structure statically determinate. Okay, then introduce force because of the removal of redundant supports. Apply Castigliano theorem to find displacement at the redundant supports. So those things you need to follow these steps. You need to follow the statically determinate structures kind of calculation. So if you have this kind of equations, you need to follow these steps. So let's see. Formulate the complete prediction, solve the equation, find the force, solve the problem using force power. So you can see here with this example you will understand. Okay, otherwise that sentence you will not grab very clearly. A beam built in at A, supported by roller at B. Okay, there's a roller. So in here you should know what are the difference between the roller support, simple support, and the different kind of supports has a different kind of reactions. Sometimes there is no horizontal reactions, only vertical. Sometimes they are both available. So that sometimes bending moments is also available. There's something like that. Things you should know at the end. I think the lecture note also there is available the supported when you change the supported conditions, supporting condition. So what is the reaction and other things. So keep it by. Sometimes it will not mention in your exam. You should know that thing. The roller at D is shown in figure 24. The beam is subject to distributed load at a point load. Okay. Apply Castigliano's theorems. This is same figure, but only there is a kind of supporting at the point D. Theorem to determine the vertical deflection at B. Only difference there is a roller support. Consider only the strain energies of bending. The strain is AI. If it is roller support is available, there is no any deflection. That is, you should know. You know boundary conditioning here. No vertical deflection, no horizontal deflection. So let's see how we can deal with this kind of questions. So you know the length A. So 0 to A and A to L, different regions. Let's see how we can deal. There is a reactions. You need to first, even though there is a roller support, this is the reaction. With the roller support, there is only vertical force FD. This is the point D. FD reactions available, and it will not move. Then at that point, deflection is 0. We already know that. Now we need to find out the FD. What is the FD value? We determine the FD values because roller at the roller point, the vertical deflections equals 0. We should know that, okay? Because with the roller, they cannot be go downward. Should be still as it is. That's why there is a reaction force applied. So then FD we will find out. Okay, this reaction we should know, but we don't know how to find out because we don't know what is the reaction at this point. So if we, because don't use the force equilibrium. Okay, P equals P plus this total load equals this one. This is wrong. Okay, because we don't know these reactions. If the fixed end, there is a bending moment and vertical and horizontal forces also. So then you can't find out if you label here horizontal force and vertical force and bending moment, you have 3 unknown and 4 unknown. Then you need to find out the 4 equation to find out the FT. That is not the thing then. So this is the unknown. These reactions we don't know, but we only know at this point vertical deflection equals 0. Then what we are going to do, find out the vertical deflection equation, and there will be FT. That equation should be equal 0. Then we can find out the FT value, the force. So that's the thing we are going to do now. So these equations we already know. The 0 to A, x equal to 0 to A, and x equal to A to L, A to capital L. So only different here you can see the earlier the point C, the midpoint deflection when you find out it was Q, now it's FD. Okay, FD x minus A, that is the length. That means somewhere here we will consider somewhere here point, general point, and this is A, this total length x minus A, this distance. Okay. So this is the bending moment. Now we need to find out the vertical deflection with respect to point point D with respect to FD. So find out the differential first derivative then. This part will be 0. There is no FD terms. In here FD, it is S minus A. Now don't do FD equals 0. Okay, this is not a dummy load. It is available there in the system. So this is not a dummy load question. Okay, there was some kind of point load. So at this point, it is best to also derive this one also, because later on we need to calculate the point B deflection. We are not going to calculate the point D deflection. We are going to find the point D deflection because of unknown reaction. We already know what is the deflection value. It is equal to 0, but we need to find out the reaction value to calculate the point B deflection. So in this calculation, we are going to find out the FD, and our questions ask, they ask find out the deflection at point B. For that, we should know that first derivative with respect to P, because point B, there is a point load downward P. Okay, so get the first derivative with respect to P using this bending moment equation. So even though this equation which you use, same results you will get, because P is only available in here, minus 6. Then find out the vertical deflection at point D. So this is the equation, and introduce the U values and with the chain rules and Leibniz rules, and then substitute in here this calculation. Sometime you need, so this is the some kind of expanding and substituting limit and all the things available in here. Okay, so you can't see with this step, everything is stepwise. You need to do the calculation separately at home. You will get this kind of answer. Okay, I'm not going to do it now. So because in here you can substitute M you will get from here M without FD. Don't do that. Okay, you need to substitute FD as well. This is M, and then dm by dfd, this one x minus A. That's the you substitute and introduce a limit after integration. After integrate them, and then it is the limits, and you will end up this kind of equation. You can see there is FD. This part should be equal 0. Then you will get the FD value. This is the FD value. So even though you can see this is large equations, those things as a value. So you will get the one value, so one numerical value. Now you have FD value. What you need to do, find out the vertical deflection at point B, du by dp. Now you know the bending moment equation. Bending moment equation, you introduce this equation. Okay? Because FD is now known thing, it's not unknown thing. Just substitute FD value. You already find out that value, and sub FD and dm by dp, it is minus x, and then differentiate with the expanding it and differentiate with respect to x. Sorry, integrate with respect to x and substitute the limit, and you will end up this kind of answer. So that's how we can deal with the kind of if you have unknown reactions, unknown things, you need to find out with the boundary condition or something like that. So we can use the Castigliano theorem for that as well. So any questions? Any questions?
Sir, can you just mention the difference between the statically indeterminate system and the determinate system?
Determinate system means we already know the values. I mean, the P. I mean, statically indeterminate means there is a load. It is not a dummy load.
Yeah.
If you remember these questions, there is FT. We know there is a load. There is a force value. Force, it has a value as well, but we don't know value. we need to find out that value. So in this here, so you need to statically that force you need to find out using this Castigliano theorem. Statically determine that in here, if they give the FD value, FD equals this value, then you don't worry. So in here they provide FD, they didn't provide FD value. They just only told us there is a reactions, and definitely we should know there is no any vertical deflection. Then we should need to find out the FD value, that force value. Anyhow, so then I explained already how we can find out it, and then we need to find out the vertical deflection at point B. Without this force value, we can't find out point deflection of this point, because when we consider the general point somewhere here, if D is available, that's one. Statically determined means that value will be provided as a function or something like that. In here, they didn't mention it, just only mention there is a reaction.
Okay, sir.
So in this case, the L-shaped beam ABCD in figure 26 has a constant cross sections along its length. Okay, the beam is subject to point load P. You can see point load somewhere here. So L-shaped, this is the different end support. This is different end support. Part A proved that the horizontal and vertical reaction H and V respectively of the pin at D are given by expression these two. So there is a vertical and horizontal force, but there is no any bending moment. You can see there is it can roll. So there is no bending moment, but horizontal and vertical force available. So that's why I told you, you need to know the type with the type of end condition, end type, the support type. You should know what are the reactions available. Are there any bending moment? So in here, bending moments also available with the horizontal and vertical force, because this is fixed end. But this is even though it is fixed end, this has a free to rotate. This doesn't have free to rotate, so there is a bending moment. But it doesn't have to free to move this direction or this direction. So that's why there is a reactions available vertical and horizontally. So there is a vertical and horizontal forces. So they already mentioned that take as a H and V, horizontal force as a H, vertical force as a V, label it. So if you label V these directions and H these directions, if you get the minus answers, it should be these directions. Okay. So label it and find out the H and V with the P. So H and P are unknown thing, statically indeterminate. So you need to determine it. You need to give the meaning for that H and V with the P, only given value P. So you need to prove this one. Yeah, they label is V directions upward, H is to right side. Okay. So this kind of questions, when you deal with this kind of questions, you can separate these two columns if you want, but always you can consider the whole sections together. But when you introduce this H and V, you can remove this hinge. Okay, because due to this supporting end, it has a reaction and vertical and horizontal reaction. That's why we need to draw this kind of end. But if you introduce these reactions instead that figure, so you don't want to again draw that one. Okay, that's why they means a hinge at D is removed and reaction force H and V introduced. So same thing will happen, equivalent thing in here now. Now bending moment DB, that means I told you they consider separately. So So you can consider this one separately and this one separately if you want. Okay. So dB, for dB, D is chosen to be origin and coordinate x is introduced. So they mention the what is the origin point and other things. Okay, the moment is given by bending moment of dB section, the horizontal part of a, so Vx. So this part somewhere here they consider. So due to this one, it is positive. So it will be Vx, okay, bending moment. And this due to this point bending moment, it will be saying minus this length will be L, so x minus L, like that. Yeah, you can see. And for BA sections, the vertical sections, B is chosen to be origin. That means the somewhere here, so origin. So we'll consider the towards these directions. Origin and coordinate y is introduced. So we are not going to introduce again x because it will be sometimes confused. That's why the moment is given by BA sections, bending moment, 2VL. That's what. So in here, okay, this is 2L. Due to this V, there is a bending moment available in here. V 2L. Okay. If you transfer this V to here, there is a bending. You need to transfer with the V force. You can mark here V with the bending moment V2L. Okay. So V 2VL, it is okay. So positive. Due to this P load, it is minus PL. And due to horizontal force, earlier in the dB section, horizontal force is not affected to the bending moment. It is in the same axis, that's why. But in in this case, it will affect. So it is again minus HL. Okay. So you can see the bending moment. Now we can get the first derivative of the moments, bending moments, with respect to H. Okay. So because with respect to H, we already know the bending moment H and B available here. The bending moment we already find out. We know the deflection at this point is equal 0. Of the horizontal deflection cannot be cannot be exceed 0 because it should be 0. So you can see DH. So DB sections, bending moments we already find out. So find out the first derivative is equal 0, and BA sections horizontal one, so minus y, and this one vertical one. So there's x. This part we don't want to consider because there's no v. And then vertical deflection BA section, it is 2L. Okay. So now we have all the first derivatives with respect to H and B. So then horizontal deflection of D is point D is find out the using BA section separately and DB section separately and get the summation. That's the thing. So then substitute here and end up somewhere here. So then what you saying D, as I told you, DB and BA separately and get the summation. So then as I told you, at the point D, vertical deflection and horizontal deflection should be 0. I already find out the answers for this one. So this equation should be equal 0. So there is a H and B, two unknowns. So you should have two equations. That's why we are going to find out the horizontal and vertical both deflections. So then you will get the two equations. So you will get the answers for those equations, H and B. So as I told you, if you get the negative sign, you can see in here they got the negative sign for the h. That means h should be other way. Any questions? So this is the I mean deep things you can expect in the exam. Find out the reactions and introducing dummy load and distribution load all together, it can be there. Any questions?
So far, no, sir.
Sorry?
For now, no.
Oh no, okay. So any others? So summary of this sessions, you should know recurrent analysis using Castigliano theorems. At least one point note should be there. So when you're going to find out the when you are going to use Castigliano theorem, there should be a point load, at least one point load, and point load at the positions where value of the deflection is required. That point load should be the point where we are going to find out the deflections. Point load acting in the same direction as required deflections. Those conditions should be satisfied. If not all those requirements are met, so if these three conditions not satisfy, at least one thing, if it is not satisfied, you need to use dummy load. That's all. So if you have any questions regarding this one, you can ask next week. So I will just explain the tutorial as well. Tutorial, then so can you see my screen?
Yes, sir.
Tell me if you have this one or different one with the tutorial as a tutorial. Tutorial 7. Is it same thing or different? Is it different? So do you have tutorial with you?
So it's the same thing.
Okay. So I will not going to read these questions. So you already identified this question now. Before this one, I told you the fixed conditions and in conditions you should know. It is available there. Let me show you. So there is so many examples in your lecture note. I couldn't find where it's available. Sometime if it is not mentioned this lecture note, maybe buckling one should be okay. So don't worry. You can refer the buckling one and the same thing, same in conditions not change with the anything, because if it is a fixane, what are the reaction available there, and if it, I can't see here, maybe buckling one. Remember, so fixed conditions, and so you can see in here, this is fixane, this is fixane. So all horizontal and vertical and bending moment available there. Okay. In here, if both 10 fix, this horizontal force, this horizontal cancel out. Okay. So bending moment is available. So in this question, I will not going to explain each and every question. Okay, you can select whatever things you can easily. Okay, if you can easily understand some tutorial, so I don't know to explain. So question one. can you deal with this one? So because I will explain one or two tutorial questions. There is so many questions. Can you deal with this question number one? So we all you already have answers with you as well. Just go through the lecture, tutorial, and you can request which one I need to explain. So you can see in here that there is a table. So you don't want to keep it mind this equation, okay? So this is a kind of the different support conditions, midpoint, the vertical deflections. They already derive the equations. So you also can derive this equation using that theory. Are you there? Which one I need to explain? Can you tell me? There was three students. Fermi, Shenal, Virant. Which one I need to?
Sir, the questions in this tutorial is bit different, sir.
That's why I asked from you. So which tutorial you should have? You have. So do you have this one? Can you see my screen now? This one?
For the first question, it's a cantilever beam with one fixed end.
Okay, so maybe I don't have your tutorial. So can you share your screen with me then? Because which one I don't have. Sometimes which one you have? I stopped the sharing screen, so you can share your screen. Shana?
So give me a second.
Do you have a different one?
Yes, I think what's shared was last year's tutorial, what they put.
This year you get new one?
This year, like there are a few additional questions also in the tutorial.
I didn't know that. Anyway.
Shall I share then?
Yeah, if you can, please.
Sir, could you give the access to share the screen?
I already finished my sharing, so you can share, I think. Isn't it? I mean, I closed my windows and need I give the additional confirmation share to this thing? I don't know.
I just don't have permission to share the screen.
Really?
It says host disabled participant screen sharing.
Oh my god. I didn't know that like that thing, but maybe settings.
Yeah.
Let me check.
I don't know. Sena, can you share the screen?
I think now you can. I changed the settings. There was I need to tick to share screen for the all participants. So I tick that.
Still, I'm unable
I think it's can now. Please try one more time.
It still gives the message host disable participant.
Oh my. Mm, Pramit, can you leave the meeting and can you rejoin? No, it's right, no?
You can see us.
It's loading. Others, I don't know. Shenal, can you see the Fermi's screen? Now I can see.
Yes, I can see.
Okay.
This is the tutorial that we have, right?
So is it different my one? I don't know. Okay. Anyway, can you go upward?
Yeah.
Because I don't have scroll access now.
Okay.
The first questions, I can't see the some of the one line missing, I think. So can you scroll to upward? Or she's gone.
Hello, sir.
Yes,
So you can see my screen, right?
I can't see. I think you didn't share it still. Okay, probably okay, I can see. Okay. So do you have any questions about the example number one? It's just sometime you didn't try for this one, but when you read this one, if you can recognize any problem with this one, can you deal with these questions without any problem? I think it's not big deal, no? So you need to find out the FA and FB. For that, you just use Q load. You don't have to worry about the indeterminate condition, because you know the total load of Q, simple Q. Then you can find out FA and FB. Am I right? For me? Fermi, Shenal, I think the one is Virant.
Yes. Yes.
So do you have any questions with this one? I think this is very familiar with this what we discuss. For me, I can't hear you. I think your mic is mute. Can you scroll down? Shanal, can you hear? Can you hear her voice? I don't know. I couldn't hear.
No, sir. No, sir.
No.
For me, we can't hear you.
Sir, she has some connection issues.
Oh, really?
Yeah.
Anyway, do you have this?
Yes, sir. What is it?
You can hear us, no? Okay. For me? For me, if you hear us, can you scroll down? Oh, if you, Shenal, if you have this tutorials, can you send me this one via email?
So shall I share my screen?
If you can, that's better because sometimes the bandwidth of the firm is low. Sometime I think that's the problem with. So, but she should close the screen, no? For that also she should hear us. Oh.
So I send the tutorial 7. Excuse me, sir.
Okay, I got it. Okay. Is the same one with Fermi Senda, Fermi Shora? I don't know. Fermi shows this kind this one. I think different one. Wait, this is different. Okay, Shanal, can you hear me?
Yes, sir.
Okay, so is this one you send me? Can you see my screen?
Yes,
Yes,
sir.
sir.
That's the one. Yeah.
Okay, so Fermi, so if you can tell Fermi, okay, I will send her message. Maybe she can't hear us. So okay, Shanal, can you send a message to Fermi to join this tutorial? I think Fermi also has different one because she shows a different one for us, no?
So this is the solutions. Yeah, these are the solutions. The
No, Fermi shows us this one. Am I right? Fermi, did you show me this one? Isn't it? Fermi, you there?
the same things. Yeah,
Same
we
thing?
have.
No, the figures are different, no? Am I right?
Yes, sir, there's another document with only
Okay, Fermi has
the
different document.
colors are not there, sir.
Okay. Anyway, so
Yeah.
you can deal with the whole question. No, what is don't worry about the tutorial number, because when I explain something, if you don't have, you're in trouble. That's why I'm asking. So did you drop the message for Fermi?
Yes, sir.
Because
Yeah.
I couldn't hear her side, because I don't know if
So she said that she'll reconnect and try.
okay, it's okay, doesn't matter. So Sena, do you have any questions about this cantilever beam questions?
No, sir. It can be. Yeah, I did it. I had no problems with that. But the eighth question is a bit difficult.
Which one?
The eighth question.
Eighth one. Okay, I will check it.
Yeah.
Second. So second one also no problem. The Viranta, do you have any questions? So this questions also similar what we discussed in the presentation. Okay, the L-shaped column. It is same. And the third one. This is good questions. If you have any question, we can discuss. And fourth one, the linear part, there is a distribution load. There's the curve beam as well. So if you have any question, you can raise your hand. Eighth one. What is the problem with eighth one? Shana. Shana.
Yes, sir. So I didn't try the eighth one. That's why.
Okay. Eighth one, there is a two curve beams are combined together, no? So in the member
Yeah.
OAB lies in one plane and has a shape of two quadrants of a circles as shown in figure 10. Okay. The radius of circle is R. At the moment MB is applied at B, somewhere here. The elastic modulus is E and the second moment of area is I. Consider only the strain energy due to bending. There are the vertical and horizontal deflection of B. Okay, this point vertical and horizontal deflection you should find out. In this case, they provide the vertical and deflection solution. So you need to consider bending moment, the two different region, isn't it? The AB sections and OA,
Yeah.
OAOBC. BA, BC, C where? They consider BC, BO I think, isn't it? It should be BO, no?
So is it OA and AB?
Oh, it's something like that.
The
Yeah,
two.
I think so. It's a little bit wrong, I think. A B B C. This should be A B and AO should be like that,
Yeah.
because in here theta, in here phi, you can see.
Yeah.
So this cannot be BC. This is there is no C actually. So it should be AO. Yeah. So then if BC somewhere here, it should be AO. Okay. So this is bending moments given. This bending moment, the plus one AB and Q is the load here. Because if you want to find out the deflection, vertical and horizontal, you need to introduce point load toward that direction, isn't it? That's
Yes,
why
sir.
this dummy load introduced. Okay, these are dummy loads, Q,
Okay.
and this is H also dummy load. So the Q, this R1 cos theta. Yeah. So, so if you are going to get the bending moment somewhere here, so this is R cos theta. R cos theta, but it is distance AB sections given by QR. Yes. Yeah, that's right. So the R cos theta means this distance. Okay. So you need to subtract. Okay, I will. Can I draw here? I think yeah. Okay. So if you get some point somewhere here, okay. So this is this length R cos theta, but you need to this distance R cos theta minus this distance. You should the total distance is R. This distance you need to subtract. This distance you need to subtract.
Yeah.
Isn't it? So
Yeah.
that's the thing they did. I think.
Yeah.
Yeah. So then you will get the this distance. R cos. Yeah. Let me check. Yeah, they consider this general point. Okay, not somewhere here. This point. This is R. Okay. This is R cos theta. So then you can subtract R cos theta from R. In here, R cos theta. Are we clear?
Yes, sir.
Okay. So then it is this value for the Q. Then H R sin theta is not. It is not problem. In here also same thing. Okay. Then what you need to do? So you need to get the difference first derivative with respect to Q and H both, because you need to find out the vertical and horizontal both. Yeah, you can see here AB section. AB sections vertical deflections with respect to Q, and this is not the BC. This is AO. AO with respect to Q, and again AB with respect to H. This is again AO with respect to H. Then in here, yeah.
Excuse
Yes.
me, sir. Can
Yes.
you explain the QR into 1 minus cos theta there?
This one. This one.
I didn't get it. Yes,
We couldn't hear properly. It's broken voice. Can you tell me again? Can you repeat it
so can you explain this? Can you
again?
explain this this
Which expression? Which one? This one?
Q? No, the QR into 1 minus cos theta. How can we obtain? How can we get this?
QR minus 1. This one, no? Yeah. Is it this one or different one? We couldn't hear you properly. That's why I'm asking.
The red color.
Yeah, circle it one, no? Circle one. Yes or no?
Yes, sir.
Okay. So that's why I'm explaining here. You can see the. So we are going to get the bending moment at this point, general point, somewhere here. Okay. So due to this Q low point load, there is a bending moment at this point, but you need to find out this distance. Okay. Here to here, this distance. But you know this is R, this total length R. If it is theta angle, so this point is with the theta angle, so you know this distance because R cos theta. So you can find out this distance R minus R cos theta. Are we clear?
Yes, sir.
So that's how we can do. Okay. Is it clear or not? Hello.
Yes, sir. Yes, sir.
Okay.
I got
Then we already find out the whole the first derivative as a bending moments. Then you can put the Q and H equals 0 because both are dummy loads. Okay, we already we introduced those load. So Q equals 0 in here. Q equals 0, H equals 0. Then it will be MB, and this will be also MB. So there is no any other bending moment. Yeah, you can see here. Then the vertical deflections, when you calculate, you need to be careful when you put the limit. Okay, in here there is no 0 to L or something because the parameter is theta. So 0 to 5/2, 0 to 5/2. Okay, the limit you can see, and other things I think it's nothing to worry. So vertical deflection when you calculate, you need to consider Q terms. In here Q1 Q terms, in here one Q terms. Yeah. Those two, and get the summation. This is superposition principle, kind of superposition. So then calculate. That's all. Any questions regarding that things? I couldn't hear your side. Any questions? So I'm not going to deal the differentiation and other things. I think it's up to you. You can do it, no? Shana, for me, Viranta,
It's clear.
it's clear.
Yes, sir.
So it is not too
Yeah.
difficult, but you are in trouble if the distribution load also available here. Then please be careful at that time. Okay.
Yeah.
So if you have past papers, those you can see here this kind of column distribution load you can easily deal, but that I'm not telling it's difficult, but you should be careful.
So if a distribution load is there in a curved beam, how can we take the centroid?
If it is a arc, normally they are not giving the triangle shape, no. So just say arc center you can take it. Okay.
Okay.
Are we clear?
Yeah. Yeah.
So Fermi, do you want to explain any other questions in here? So someone else? Viranta? So did you try out these questions? I think this is good one. Okay, you can see this is not a linear increase. This is the increase until midpoint. Then again it will be reduced. Okay. So this is kind of this is also symmetric. So maybe you can consider one side. Yeah, you can see here they only consider one side, half of beam, because this is symmetric. Okay, so if you saw some symmetric thing, so in here also you can consider one side. If it is same, consider both sides. Okay, yeah, you can see it's half of beam. Okay, and finally when you do the calculation you need to multiply by 2. Okay, you can see in here they will put the 2. Yeah, otherwise it's wrong. Okay, keep it in mind, if you get the symmetric figure, if you get the one side at the final calculation you need to multiply by 2. So I'm not going to in detail explain everything because I already explained 6 or 7 example at the lecture also. So if you want, I can explain. Otherwise, I will stop here. Anyone? For me? We couldn't hear you long time. Can't you hear until now? Okay, you can hear. For me?
Yeah, I
Do you
heard
have any
it,
questions?
sir.
So you told
No,
me
sir.
at the very beginning you had a problem with the curve beam. I mean the Castigliano theorem.
Yeah.
So still,
Yeah, that's
do you have
okay
that
now.
sense? Or is it
No, I
clear?
had the doubt with the dummy load like where we are going to set it to 0. So now I understood that.
You understood, no? Okay. Sena, still do you have anything to clear?
No, sir.
Okay. Viranta,
No, sir.
so do you want to discuss any questions furthermore?
No.
Okay, so try out the questions at the home then. So I will inform next lecture when we are going to do. Maybe it will be same week, because I'm going to plan to finish the whole lecture before. What is your final date of this semester? Do you know that?
June 5th, and
Sorry.
5th of June, I think.
Okay,
5th
so
of
I need to
June.
finish it before that. No, so I will do the next two lessons very quickly. So I hope you don't have any questions until this lecture. I mean, we already cover 8th lecture, so only we have 2 lectures. We only have 2 lectures. Buckling lessons is not too long one, so I will finish very quickly. And thick wall cylinder one is a little bit lengthy session. Even though your lecture note also you can see it's a lengthy one, but I think theory is not. If you understand the theory, it's not lengthy one. So the calculation part very lengthy. That's the problem. Yeah, so we will cover before. Okay, within next 10 days, I will cover the whole lecture. Okay. So if we have any questions, don't wait until the day before the exam. So raise your hand and ask questions. Okay, you can contact me via email. Sorry for last week. I had some personal things and I busy with that one. So I hope you already select your groups, everyone. So there is only few students. So I want to give the notice. There was a small issue. So if you have any problem with this assignment, you can email me. Don't email to the Dr. Ian, because so I will email to him and ask the raise your voice. Don't email to him, because so I heard Dr. Ian told me there's one student, he got the email from him, and I got email from him as again, and I emailed to Dr. Ian, and he told me I got this email from that particular students, so that is not good, something like that. So he told that that is not professional. So if you want to email him and myself both, so what you need to do, you can CC me to the email. Okay, don't email don't separate email to send both this, I mean, even though same content, don't put the separate emails. Just for your understanding, I'm telling you. So if you want to know that email, you're going to send to the Dr. Ian. No, if Dr. Ian, if you want to inform to Dr. Ian, I send the email to the I mean, if you're going to email to the Mr. Harrison, so what you can do, you can CC he or myself. Don't send it separate two emails, because we will reply. If you reply, if we reply two separate answers, I mean replies, so you also will be confused, because we need before we reply to you, we will discuss and we will finalize one thing. I mean, we will get the one conclusion and we will reply you. So that's the thing. So fortunately, I didn't reply to that students, and I asked from the Dr. Ian. Then he told me he already gave the solution for this one and something like that. So I'm not going to name his the name his name in here, mention his name. But that is not good. Okay, for me, Chinad. So can you forward this message?
Okay.
So
So
I
if
think
someone needs to send a mail,
I'm sorry.
if someone needs to send a mail, he or she should CC to either Arshana sir or Dr. Ian.
Yeah, so I mean, otherwise, that's
Is
not.
it better if they can send the mail directly to first to you?
Yeah, then if
Then
there is a if I can't solve that problem, I will send to the doctor and I will ask. So if I can solve this problem or matter, so that's not good to send to that doctor Ian because he's also very busy. So
yeah.
so small reasons sometimes not considerable thing. That's a problem. Okay, I hope that there is only 30. Everyone got the group, I think. So I can't ask now because so many students not available in here. But I hope everyone got. Don't tell now I don't have group or something like that. There is a 7 group, I think, 35 students. If there is another 31, 30, and 36 one, so we don't have group because he or she should tell early. Anyway, good luck with the assignment as well. So if you have any questions regarding the uh, assignments, email me. If I can't give the solution for it, I will forward that email to the doctor and I will look for the solution for that one. Okay. Okay, Anna.
Okay, sir.
Okay. Good afternoon. Okay. Good afternoon. Okay.
Okay, good afternoon. Thank you, sir.